David Williamson Shaffer was awarded his PhD from the MIT Media Lab. Then he had a spell teaching and researching at Harvard Graduate School of Education. And he's since risen to be the Villas Distinguished Professor of Learning Sciences at the University of Wisconsin-Madison. He is a data philosopher at the Wisconsin Center for Education Research. I think that's a new profession. And he is the Obel Professor of Learning Analytics at Aalborg University in Copenhagen. David's mission is truly transdisciplinary. He wants to harmonize qualitative and quantitative methodologies in a way that scales for the era of data science in order to yield rich insights into behavior that is cognitively and socially rich. So who better to ask to come to LAK, a community where the expression deep learning still means humans and machines. His work on quantitative ethnography has been met with acclaim from educational thought leaders. James Paul Gee sees it as, quote, ringing the bell to announce that the data revolution is coming to education and the social sciences. Here we get numbers and meaning both, and they don't fight each other. They give us innovative ways out of our old ruts. At LAK, we're all about figuring out how the quants can talk to the quals in effective ways and overcoming the traditional sort of silos between those disciplines. And we think David has some of the important pieces of this puzzle. So please switch off your mobiles and join with me in giving David a warm welcome as he speaks to us on the importance of meaning, going beyond mixed methods to turn big data into real understanding. David, thank you.
Thank you very much, Simon, for that great introduction. And thank you all for coming early in the morning to the first session. What I'd like to talk to you about today is scarcity. Now, there are lots of versions of scarcity in the world. There's food scarcity, there's scarcity of energy and petrol, there's scarcity of water. One of the interesting things about scarcity is that in almost every instance when there's a scarce resource, nature adapts. Plants in the desert learn to go dormant for many years and spring up when there's water available. They spread the seeds that germinate in 5 years or 10 years or 20 years in order to assure their survival. The scarcity I want to talk to you about today, though, is a different kind of scarcity. It's a scarcity of data. So for a very, very long time, data was hard to get. Tycho Brahe, for example, spent his entire life observing the heavens, trying to collect data about the motions of the planets. When Ronald Fisher first invented hypothesis testing, data was hard to come by. When Clifford Geertz was writing about thick description, data was something that ethnographers spent years in the field to collect. Data was scarce when Barbara Entwistle helped develop the first multi-level linear models, and it's scarce when Emma Tarlow did her landmark study on the secret lives of hair. Different traditions, qualitative and quantitative, have had different ways of addressing this problem of scarcity. In the qualitative tradition, researchers collect data about only a very small number of people, but they collect a larger number of data about a smaller number of individuals in order to be able to understand how and why people are behaving the way they do. Quantitative research does have a different solution. They collect a lot of data about a lot of people, but as a result can only collect a very small amount of data. In other words, both quantitative and qualitative data and data analysis grew up as a response, an adaptation to scarcity. This is actually a problem today, and the reason that it's a problem is that we don't live in an era of data scarcity anymore. Right? And the challenge in the era of big data is to try and find a way to make sense of all that data. And what I'm going to argue today is that qualitative methods alone are not enough to make sense of this data, and quantitative methods alone are not sufficient to make sense of this kind of data. We need something different. Hopefully not just that. So now, it might seem at first blush like it's a little strange to say that large amounts of data is a problem for qualitative researchers. Qualitative researchers are used to just collecting data about a small number of people. So what if there's extra data lying around? I don't necessarily need to use it. I can just use the small amount of data that I choose to use. Well, there's a couple problems with that. One is that it makes analyses underpowered. We're essentially leaving data on the table that we haven't made use of. Worse, though, the fact that there's tons of data out there and I'm only selecting a small subset of it leads to confirmation bias. More common term is cherry picking. Right? I'm finding the specific examples that are making the case that I want, and it's not just that I'm ignoring the other data, it's that I'm selectively ignoring it. Similarly, you might think that quantitative analysis doesn't have a problem with more data. I mean, the purpose of quantitative analysis, right, is to look at some small sample of data and determine whether we can generalize to some larger population. It's all about essentially controlling for false positives or type 1 errors. There's some other things too, obviously. It's about determining whether we have a p-value that's sufficiently small, again, somewhat metaphorically. So you might think, well, that's great. More data means larger samples. Larger samples means I'm more likely to find an effect that's statistically significant. Here's the issue, though. Statistical significance actually depends on a particular relationship. It's a relationship between p and n, that is, between the level of significance and the size of the sample. As the sample size goes up, all other things being equal, p goes down. Sample size goes way up, p goes way down. In other words, a statistical method that was adapted to scarcity was designed to determine whether or not we have enough data to make a particular claim, has problems when there's always enough data to make a claim. Now, another way of thinking about this is that an important part of any statistic, this mic is sort of catching a lot of P's there. An important part of a statistical analysis is understanding how much of the phenomenon we actually explain. And so typically we quantify this with something like an r-squared value, which tells us the amount of variance that one variable, the amount of variance that in one variable that's explained by another. So for example, weight and height have an r-squared of about 50% for normally healthy people, which means that half the differences in people's weight can be accounted for by differences in their height. Similarly, wealth and happiness are related with an r-squared of about 0.25. So 1/4 of people's happiness can be accounted for by their wealth, although of course we always have to be careful because it's also true that 1/4 of people's wealth can be accounted for by their happiness. This is of course the basic phenomenon of correlations, and we can use this idea of the amount of variance explained to understand the impact of interventions. So for example, John Hattie has compiled a number of effect sizes across interventions in education. So teacher feedback, for example, has a 24%, can account for 24% of the variance in student outcomes. Peer tutoring only about 6%, simulation in games 3%, and so on. Even if these numbers aren't exactly correct, they certainly give us an order of magnitude, right? These things are significant. Teacher feedback, not surprisingly, is incredibly significant. To put these numbers in scale, by the way, one grade level, that is the change in somebody's expected understanding over one year of school, it's about 6%. It's kind of a depressing number if you think about it. 1 year of my growth in school is about 6% accounts for 6% of the change. The reason for this is actually that standardized tests are normed to have an effect size of 0.5, which correlates to a percentage variance explained of 6%. The reason all this is important is that this formula isn't actually quite right. The formula actually has the r-squared in it as well. So as n goes up, it's true that p goes down. As n goes up a lot, the r-squared starts to go down. In other words, we start explaining less and less and less of the phenomenon of interest. I'm going to give you a few examples of this. So one thing that's pretty clear is that Google knows more about me than any learning management system will ever know about any student. It knows where I go, it knows what I eat, it knows where I sleep. Right? And with all of these sophisticated analytics, right, Google, whose job it is to provide ads that I'm going to click on, right, the best that they do is the last time I searched for a garden hose because we ran out of a garden hose, well, you know, they showed me books about gardening. And they showed me movies about gardening. not really particularly deep analytics. Think about the number of ads you see if you don't use an ad blocker on your machine and the number of them that you actually click. I ran a little experiment because I have a book that's just out, so I went on Amazon and I put up an ad account, right? And I did it in a number of different ways, just trying different permutations and combinations. And I got an incredible number of impressions, right? On my last ad, 25,000 people saw an ad for my book. That sounds really great until you look at the actual number of people who clicked. Right? And the reason that this is such a problem is that Google, right, who has the best analytics that are out there, the best minds working on this, right, is only able to be right. Well, I don't even want to calculate what those percentages are. And in the field of education, this is a particular problem. So imagine that we had the best feedback system in the world ever, and it provided all kinds of feedback that teachers could use to pass to their students. But it turned out that it was almost never right. Teachers, thought leaders, principals would essentially not just throw away that particular system, they'd start to think that the whole field of learning analytics was barking up the wrong tree. Second example. Here I'm actually drawing from some work that was presented at this conference some years ago. I'm not going to tell you who it was because the point isn't to be critical of a particular person or of a particular study. This was a group that was looking at Dragonbox. For those of you who aren't familiar with it, it's a fantastic computer game. You learn algebra by essentially manipulating symbols on the screen to get points and grow dragons and so forth, right? So in this case, you would take the 4 and you would drag it across to the other side to start simplifying the equation. To give a kind of quick overview of the study, they looked at data from 24,000 students. They had 21 million data points because, of course, each student is doing many things as they're playing the game. I'm looking at 540,000 different moves that you could make in the game. So things like adding something on both sides, subtracting something from both sides, subtract something with merging, and so on. Right? And they used an extremely conservative p-value, all things considered, 0.001. Well, now, let's just make one quick observation, which is that if you have 540,000 moves that you think might be important, and your p-value is 0.001, well, 540 are likely to be statistically significant just by chance alone. But worse, if you run the numbers, a study with this design is likely to account for 0.00025%. Or if we translate that back into the amount of schooling that would account for, well, it's about 1.4 seconds of instruction. Okay. Third example, this also again from a previous LAK conference. This was a group that was looking at the PISA results, where interestingly, girls perform better in mathematics than boys. Finland is one of the few countries for which that's true. And they were trying to refine their analysis by using data mining techniques. I won't bother you with the details of the study, but let me read one part of the conclusion. So their conclusion was, students who are socially and economically less advantaged have high anxiety towards mathematics and low self-concept in mathematics, but still clearly above average attitudes towards school are girls who perform below level 3. I've used this slide a lot at conferences, so I've read this many, many times. I have no idea what that means or what I would possibly do with it. Final example here. Right? If I did a statistical analysis of chess playing, I looked at good players and bad players, and I threw in every possible metric I could think of, well, the single most important thing I would discover is that most important difference between experts and novices, experts move their pieces faster. And the single worst piece of advice that you could give to somebody learning to play chess is just move your pieces faster. In other words, as a field, we think about the fact that we have all this big data and all of these powerful tools as a process of data mining. And here I'm not picking on the EDM community specifically. Right? That is, we have all of these mountains of data, and we have sophisticated equipment that we can use to extract information. But in fact, as these examples suggest, it's very easy to fall into something that looks a lot more like data prospecting, where you find stuff that's in the world, you sift through it, and you hope to find some tiny nuggets that might be useful someday. In other words, what I'm arguing is that whatever this new form of big data research is, it's going to have to be about things that are important, that we actually care about. It's going to have to understand what those things mean and what we can do with them. And we have to know that we're not just looking at isolated examples in a huge mountain of data. For this reason, I suggest that a good place to start thinking about this problem is the field of ethnography. As many of you probably know, ethnography is the science of studying cultures. It's the science of understanding things that are important to some group of people and what those things mean to them. This is a particularly important perspective to take on learning in an age where learning basic facts and basic skills is clearly not enough. People need to learn to solve complex problems that exist in the real world, and typically problems that are solved not just by one person, but collaboratively, either in cross-functional teams or in teams with deep expertise. In a world like that, learning is fundamentally a process of enculturation. It's becoming part of some community of practice. Or as Jim G. describes, it's acquiring a discourse, big D discourse, which is some socially accepted association among ways of talking, ways of thinking, ways of feeling, ways of believing, ways of caring about within some community that's important in the world. Let me just give you a quick example of this. So that all sounds very abstract. I'm from New York City, just like Ali Wise. And at least when I look at some patch of dirt on the ground, I'm really only thinking one thing. Is it wet enough that if I step on it, my sneakers are going to get muddy? Because that was my entire experience of dirt as a kid. But as anthropologist Charles Goodwin points out, when an archaeologist looks at a piece of dirt, they're looking at it in a very different way. They're looking for things like post holes, evidence of past human civilization that they can read in the present condition of the soil. They do this, of course, by carefully looking at the soil and testing it. They grade its color. They actually grade its taste, which I think is a little revolting. But in other words, an archaeologist sees a connection between soil, between tools like the Munsell color chart, which is the standardized chart for grading soil colors, and of course, evidence of human activity in the past, like post holes. All of these things, post holes and Munsell color charts and soils, are called codes. And all a code means is that it's some culturally relevant and meaningful part of a discourse. It's something that people see in the world that they care about. In other words, the process of enculturation is a process of learning the codes that are part of a discourse in order to understand a culture. So in other words, part of learning is about learning the different codes of some community of practice. Beyond that, though, I've argued that being an archaeologist isn't just a matter of understanding soil and Munsell color charts and post holes. It's understanding that you use a Munsell color chart to analyze soil, and that the reason that you use the Munsell color chart to analyze soil is so that you can identify things like post holes. In other words, there's a set of connections among the codes. If learning is a process of enculturation, a process of learning to see the world the way some particular group does, to develop what I've called an epistemic frame, when you learn to see the world in some particular way, you have to learn the codes and also the way those codes are connected to one another. In other words, the process of learning is a process of understanding what people see, how they understand the relationships between those things, and therefore how they think as a member of some community of practice. Let me just pop back for a second. I just want to show you some data. It happens to be from my own work because I have the data about how this works. I'm going to show you some data from a simulation called Rescue Shell. In the simulation, students work in teams to develop a robotic exoskeleton. The way the simulation works is the students first break up into teams where each team focuses on one smaller part of the design problem. And then they come together in the classic jigsaw so that in the new teams, they have all the different expertise that they need. So in this case, what we see is the team's mentor, their design advisor, asked everybody to introduce themselves. The students all introduce themselves, right? Say who they are and which team they were working on before, which part of the problem they were working on before. The discussion takes a turn when one of the students, Daniel, asks about the actual results that the other team members had in their previous investigations. And then we see a series of turns of talk where the students are talking about the technical requirements that they were meeting and how their devices performed. So Zachary says that safety was close to the company requirement. Daniel says they were able to reach all the internal consultant requests. Gabrielle says not just the things that were required, but also their preferences and so on. conversation takes another turn when Michael gets more specific and actually asks, what were the results of your best prototype? He's asking for the data. And then we see a series of turns of talk where the students are talking about data. They're talking about the actual payloads of the devices they developed, the agility, the recharge interval, the cost, and so on. Zachary takes a step back and sums this up by saying, essentially, well, it looks like every device performed well in some ways and not so well in another. And that leads Elizabeth to start talking about the design trade-offs, which are, of course, the key part of any design problem. She's saying, well, we need to figure out what's important to us so we can decide where to make these trade-offs. In other words, just in this little snippet of data, what we can see is a relationship between technical requirements, data, and design trade-offs. In order to make a design, the students have to figure out how to make design trade-offs based on the technical requirements of the device they're creating. But in order to do that, they first have to start talking about data, and then they can use that data to make the design decisions. Now, let me make a couple of observations just about this brief snippet of qualitative data that I've shown you. So one of them is that in order to tell that story, I actually had to point at specific things in the data. I had to show you where, for example, Gabrielle was talking about technical requirements, and where later on she was talking about data. Now, again, there's nothing particularly magical about this. Researchers do this all the time in a code book. You identify a code, provide a definition, typically you provide some examples, you repeat for all of your codes. In other words, a code book plays a critical role in this process, because what a code book does is it takes us from the things that happen in the world, the actual discourse, and our record of the discourse, field notes, log files, whatever it is, and lets us go from there to what we're interested in, which is the culturally relevant and meaningful aspect of a discourse, the big C codes. And we do this by identifying what we might call small c codes. That is the things that count for evidence or warrants that the big C codes are there. In other words, this code book provides a critical step in connecting the small c codes, the things that we can see in the data, to the big C codes, which are the things we want to tell the story about. In other words, our code book is the bridge between the world of data and the world of interpretation, which is where we want to go. We can understand the structure of a culture, the way people are making meaning, by looking at what happens in the data only because we can make this translation. Which means that the code book plays a critical role in doing meaningful analyses. That's why, in addition to the big C code, the thing that we think is meaningful, and the small c code, which is the way we identify it, and perhaps examples, we also need to validate our codes in some way. We need to make sure that, in fact, we're pointing at the right things. This is typically done using inter-rater reliability. In my field, we tend to use kappas. There's lots of other ones, precision, recall, F-statistics. You could go down a long list of them. And what's important about the inter-rater reliability statistic is that you don't just compute the statistic on some small sample of data. You actually have to warrant that your sample, that is the test that you've done, generalizes to the data as a whole. Let me just explain quickly what I mean by that. Right? We all get that if I have a sample and I want to generalize to some larger population, I have to control for my type 1 error rate. Well, coding that I'm doing inter-rater reliability on is just a sample. It's a sample of all the possible things that those two raters could code. And almost nobody ever does controls for type 1 error. We've actually done meta-reviews of the literature, and it almost never happens. The reason, by the way, is that these inter-rater reliability statistics have very non-normal distributions. It's actually very hard to analytically determine what the distribution is. And as a result, it's difficult to conduct a type 1 error test. So we developed a Monte Carlo rejective method, it's called RHO, that essentially is able to control for type 1 error in these kinds of statistics, and actually in any statistic that doesn't have a known a priori distribution. It's a Monte Carlo method, so it's a version of like bootstrapping. In other words, we can determine not only what the rate of agreement is, but that's in fact statistically significant. And this matters actually because when we've looked at, used a Monte Carlo simulation to look at coding, we get error rates from typical processes of coding as high as 11 or 12%, and for codes that occur infrequently, as high as 30 to 35%. So just stop and think about that for a second, right? Whatever statistics you do after that, if 30% of the things that you have identified as the important variables are wrong, your statistics probably have a problem. In other words, we can take this critical link between what we see in the data and the interpretations we make, a link that is, whether that link has been done by looking at the data and inferring a code in a qualitative sense, or using some kind of topic model or something else and then validating it. We have statistics that can make sure that we're essentially not just putting garbage in and getting garbage out. Now, there's another thing we should point out about this little example that I gave you, and in particular, it's one little example. Right? We have no idea whether this particular pattern that I just showed you occurs once, occurred twice in all the things that the students ever did, occurred hundreds and hundreds of times. In other words, my little story is essentially a sample. It's an extremely small sample. Right? And the question is, does that generalize in any way within the data? Right? If I were to look at more and more of the data, would I see this pattern over and over again? In other words, if I'm trying to make a claim about the way in which some particular people within some practice have made a set of connections, and I have to find some way of actually modeling that in order to test it. Well, if I want to model the way in which people make connections, one of the things I have to do is figure out how to model a connection in the first place. So let's look at one connection. We actually have seen this already, right? We saw a connection between data and technical requirements. For example, when Michael was asking about data earlier in the example, he was doing so in the context of people talking about technical requirements. So this is, in a sense, a connection between data and technical requirements. Students sometimes do this within one turn of talk. So for example, Thompson, at another point in the data, talks about data, the payload, agility, and so on, and at the same time talks about the technical requirements, right? So the connection can be between students or within the thing that one student says. Well, this gives us a pretty good way of understanding how people are making connections in the data. We can code the data, and then we can look at each line of data and look at the things that happened just before it and see whether there are any connections. We can repeat the same thing for the next line, and the next line, and the next line. And we don't want to go back forever, because what we're really interested in is the recent temporal context, the place where people are holding the same ideas in a common ground. And as we go through, we can see places where something that one student says is in the context of something that another student said. So here's a link between technical requirements and data. We can represent these kinds of linkages as connections in a network. So for example, that turn of talk I just showed you might have a network like this. Other turns of talk would make different connections. Some of them might make more than one connection. If I looked over and over and over again in the data, I would see that some connections get made multiple times, kind of reinforcing the connections in the network. And ultimately, for each student or each group, I could produce a network that represented the structure of connections that they made while they were working. This is called epistemic network analysis, and it's essentially the process of constructing a network that shows the connections, the enculturation of people as they're working on solving a problem. I'm just going to show you a quick video. I think it's a little less than 2 minutes. And it's just it gives a kind of illustration of this process in a way that's a little easier to follow than just me kind of showing you all kinds of diagrams popping around. It's actually a scene from Law and Order. You'll see the scene twice. So the first time it'll be with transcript. So imagine that that's like the log file view. And then the second time through, you'll see the same scene, except that you'll see the epistemic networks as they develop. So here we saw a conversation among 3 people. It was pretty clear that they had different perspectives, and now we can actually get a representation of how those perspectives differ. By the way, it turns out Olivia was right, and it was the baby's father. But in any case. So we can use a similar technique to look at the group that we were just looking at, that is to construct the networks of connections that the group made. Here it is. You'll notice, by the way, that this more or less illustrates the hypothesis that we had. If it's hard to see that, just imagine it like this, right? In addition to looking at the group as a whole, we can also look at the individuals in the group. So, for example, we can look at Michael's network of connections. And as you remember, Michael was the person who made the move from talking about technical requirements to asking about the underlying data. We can look at, and you can notice that Michael's point is kind of up and to the right in space here because the connections that he's made in the network are up and to the right. Similarly, Elizabeth, who, as you recall, is the person who actually went from the discussion of data to the discussion of design trade-offs, has a point that's lower down in the space because her strongest connections are lower down in the space. So now, in addition to just looking at one group of students, we could look at all of the students who were in the same simulation at the same time. One thing I didn't tell you is that actually this group of students was a more advanced group of students, meaning it had some engineering experience. We also had a control group, which was a group of students who had almost no engineering experience. And though some of you may be wondering, by the way, like, where are these points coming from and how is the network placed in the space? The idea here is that each person or each group has a network. For each of those networks, we can compute the centroid, or the center of mass of the network. Different networks have different centroids. And essentially what we're doing is we're taking the co-occurrence matrices that represent the networks, we're projecting them into a high-dimensional space and doing a dimensional reduction down to 2 dimensions. And then we optimize the positions of the nodes in order to create this correspondence between the centroid of the network and its position in the high-dimensional space. I'm happy to talk more about that later. I didn't want to bog us down too much in the math. In any case, what this means is now we can ask questions about whether the difference between, in this case, two groups is statistically significant. It turns out in this case that it is, and actually with a pretty good effect size. We can also, but in addition, we can now look and see, well, why are these groups different? Well, here's the network, average network for the novices. Here's the average network for the experts, or the more advanced students. We can see that they're different, and actually if we subtract the two, we can see how they're different. The novices focus more on technical requirements and collaboration. And if you stop and think about it, this makes sense. You take a bunch of people who don't know anything about engineering and you give them an engineering problem, the first thing they have to figure out is what are we supposed to do and how are we actually all going to do it? Because the more advanced students have had experience with this before, they can focus more on the data that is the linchpin in solving the design problem. But of course, we've gone from a group of 5 students to a whole class of students to a comparison study. We've actually done this over and over and over again with groups of students, and we can compare those in a similar way. And as you can see, if you look, there's a white mark on the slide there, but as the number gets bigger, the differences are statistically significant, but now those statistics are actually grounded back in the original data. So this is a very particular model, right? It's saying that we can see a set of relationships between the codes, and that generalizes in the data. And we can measure that statistically. But it has an important property, which is each of these points represents a network. So if I want to interrogate why that point is where it is, I can go and I can see its network and see what connections that person or that group was making. More than that, I can actually look at any one of the connections and I can go back to the data and I can see the specific places where those connections were made. In other words, this is a model that has an important property of being able to go from the model back to the original data and see how the model was constructed and whether the interpretation that I have based on the model makes sense in terms of the original data. This is something that referred to as closing the interpretive loop. That is, we go from data to model, but then we can go all the way back to the data again. What's happening as a result is that we have 3 critical places where we're asking a question about the validity of our model. We're asking a question when we go from the small c codes to the big C codes. That is when we say that what we're modeling is meaningful. We can look at whether the pattern of connections that we're describing that as part of this culture is in fact meaningful. And we can look and see whether the resulting model is meaningful in terms of the original data. And in at least 2 of these places, we can use statistical tools to support that analysis. Now, I just want to emphasize that this is not the same as ordinary mixed methods, right? So in a mixed method study, you might look at the data and come up with some model of the data and some statistically significant pattern. And then you might go and look at the data and see whether or not some way of looking at the data confirmed the original pattern, right? So this is kind of the process of triangulation. What's happening here is that the 2 things are intimately connected with one another. The model came out of the qualitative research and the qualitative examination is simply the local instantiation of the model. The two things are isomorphic in a way that they're not in a typical mixed method study. And I've called this quantitative ethnography. And turns out, as you might imagine, there's actually a lot of stuff you have to do to take kind of the messy qualitative data, conduct an analysis that makes sense in ethnographic terms, also be able to model it, and so on. And the book is more or less about that. But whether we call it quantitative ethnography or not, the important point here is that if we want to do good research in the age of big data, certainly good research about learning, we need grounded models. That is, we need models that actually come out of an understanding of the data and not simply a pattern that we found, because we can always find a pattern if we have enough data. We need to make sure that those models are constructed out of meaningful variables. Why? Because if our variables don't mean anything, if the codes don't mean anything, then it doesn't matter whether the model is statistically sound. And finally, we want things that aren't black boxes. And we want them to not be black boxes because we want to be able to understand how the model was produced and not simply, like in the example of chess, say, well, there's this pattern here and not be able to do anything with it. Now, to be clear, the example I showed is using a technique called epistemic network analysis, and people have used, including me and others, have used epistemic network analysis to look at engineering and urban planning and journalism and surgery and medical clinics and gaze coordination and intranet search and a whole bunch of other things. But there's nothing particularly unique about E&A in this context, right? We can use techniques like hierarchical linear modeling, topic modeling, and so forth to do the same kind of work. Like as a quick shout out, so Ali Weiss, who's in the audience here, has done work that I would say is an excellent example of quantitative ethnography, even though she didn't use E&A, she didn't call it quantitative ethnography, but the same principles are still applying. I should say something else, of course, which is that there is a different mode of thinking about statistics. It's using exploratory models. So I'm not actually worried about whether or not this has a grounded meaning. I just want to kind of see what's out there. It's like I'm on a fishing expedition. And sure, once I find something, I have to go about it more rigorously and make sure that things have the meaning that they have. But it's a lens for looking at the world. And exploratory models are great, and I think we should continue to use them. But they also remind me a little bit of the Curio movement at the 2 centuries ago. So essentially what happened is Western Europeans started sailing all over the world, and once those voyages became safe, rich Western Americans started tagging along and collecting stuff. They'd bring back skulls and shells and strange lizards and stuffed finches and things that they would just collect and literally just display them as a bunch of stuff. Look at all the science I have, was essentially what they were saying. In other words, 2 centuries ago, in this kind of purely exploratory mode, people were developing a data explosion. There was much more information about the natural world than we'd ever had before. What transformed this Curio movement from something that was essentially a curiosity, the two words are related to one another, was the work of people like Charles Darwin, who actually was one of those rich young men who was traveling around in the HMS Beagle gathering stuff. But of course, what Darwin did was synthesize that information into a theory, into an understanding that was going beyond just the exploratory work and was thinking about how it is that all these different pieces connect up in some systematic way. And I think that what has happened up to now in a lot of movements that are looking at big data, it's not just true in learning analytics, although I think it also is true here, is that there's been a certain theory scarcity. We've had an abundance of data, right? And we've done a bunch of exploration to figure out how can we actually get a grip on this data. And I think it's now time here and in many other places to move to the next stage where we focus more than we have in the past on the importance of building theories, on the importance of those models being grounded, on the importance of those models being meaningful. I say this in part because I'm not the only person in the community who's been writing about this. Shane and Dragon and Simon and Ruth and Ali and Bodong and a whole bunch of other people have been talking about the importance of this in our field. It's timely because we're at a place where if we keep doing this, right, the field is going to be discredited. Right? We need to do analyses that are theoretically sound and that are meaningful as a way of building interfaces that students and teachers can use that will actually help them in their work. In other words, as we move from the age of just having a lot of data to understanding it, we have to combine qualitative and quantitative approaches in ways that give us results that are both statistically significant, meaning that they're not just cherry picking, and are meaningful. And what I've tried to present here is one framework for thinking about that, through this lens of quantitative ethnography. By combining a science of meaning and a science of generalization, we can produce a set of tools and approaches that let us solve this very important problem in the field. So I'm going to stop there, even though I only got the 5-minute hook, and I had technical problems. Just give me some credit. No, I want to end by thanking the sponsor for this work, the National Science Foundation, the principal sponsor. There have been some others. There have also been a tremendous number of people who have contributed to this work in various ways. This is not even a complete list, and it certainly doesn't count all the people that I've had conversations with along the way who have influenced my thinking. Simon and Danielle and Shane and a whole bunch of other people in this room. This group of collaborators includes some people who are actually at the conference today, and please feel free to seek them out if you'd like. I'd also like to thank the Solar for inviting me to be a keynote. And I'd like to thank our tech crew here who saw us through troubled times. And I'd like to thank all of you, both for coming and listening today and for being part of what I think is an important effort to create an integrated science of how we understand and model meaningful learning. So let me stop there.
Thanks so much, David. And you've left time for some Q&A before we finish this session, before the break. So I think we have someone with a microphone, but if not, then we'll perhaps just repeat the question so it's on the recording. So who'd like to kick off?
Pip.
Thank you, David, very much. I really love the way in which you framed this, and quantitative ethnography is fabulous. I have a question about the epistemic network analysis. And I understand, and I'm an ignorant questioner, so please forgive me. You're clearly coding the network connections through the temporal association between the things that you've coded. Presumably that's a choice you've made, and there would be other ways of doing it. You might want to code them directionally, or you might want to attach some kind of meaning for the linkage from one thing to another. Is the decision to stick with the simple association coding based on exploration of a whole lot of other possibilities and it turns out to be the best, or is this a world to be explored?
So if I can just summarize, the question was, that was a great talk, thank you. And there was a specific question about epistemic network analysis that I'm just trying to summarize. Which was that the epistemic network analysis is capturing one feature of the discourse, which is its temporal collocation. It's not capturing other things like directionality or the specific nature of the link and so on. The way the question was framed is this, have you tried a whole bunch of other stuff and this is the best way to do it, or is this the first foray into a new world and there's lots of things to explore? And the answer, of course, is some of both. What's important about, I think what's important about that set of choices that go into doing the network analysis the way they've done is that it reflects a particular theory of discourse, right? So it reflects the idea that people make connections to other people, that the connections are in fact what we're interested in, and that those connections happen within some temporal span. So that's the heart of the theory that ENA is trying to capture. There are some reasons why a simpler model is preferable to models that explore some of the other features that you've just described. So, one of the things that you see in the world of concept mapping, for example, is people say that the directionality of the links is really important, right? That the heat is caused by the sun. It's important to know what the link was. Of course, the way that most languages work, you could also say, the heat is caused by the sun, so the sun causes heat, and you run the link exactly the other way. So there are some situations in which the directionality it could be problematic, right? But that doesn't mean that if you had a situation where you thought that the directionality was important, that you wouldn't do it that way. We actually do a version of E&A where instead of looking back in the conversation, we look forward, and that's a way of capturing the downstream effects of something that somebody said. It's a different model, different theory of discourse. It's more closely to what Ali was doing in the study that she was looking at. There are all kinds of compromises that we make because, frankly, natural language processing isn't as advanced as it should be. So in order to do something at scale, we make some compromises. So there are reasons why it's evolved the way it has. I should also mention that the visualizations are really important, and the more complex you make the model, the harder it is to capture that in the visualizations accurately. But in any case, yes, there are some reasons why we've done it. We have looked at other things, but there are definitely other things that people can and should be doing, either with ENA or with some other tool, some kind of pattern mining or something as a way of getting at directionality, or sequence mining that ENA doesn't do.
Okay, thank you. Yeah, we've got one up there. Have we got a microphone that can get up?
I'll try to speak very loudly.
Okay, thank you.
You mentioned in your talk exploratory models, research, and that is very important. Now, opposite exploratory research is confirmatory research. What would you say are the requirements for doing confirmatory research?
So that's a good question, and there's actually, of course, a whole field of study about the difference between confirmatory and exploratory research. Sorry, the question was, I've talked about exploratory research, I talked about, and the obvious opposite of exploratory is confirmatory, and how am I seeing the relationship between those? It's interesting because in the world of ethnography, the terms confirmatory and exploratory aren't really used. Clifford Geertz talks about the idea that when it gives the example of a doctor, right? So when I go to a doctor and the doctor says, I think you have measles, it's not really either confirmatory or exploratory, it's diagnostic. He's making a claim about something that he sees. So there is another class of models in between those, and quantitative ethnography tends to sit in that space. But what I would say about confirmatory models is that they should be based on, so you could do a confirmatory model where you are only looking at the data and you are not doing all of this paying attention to meaning if you have done this kind of diagnostic model first. But ultimately, if your confirmation isn't grounded in something that's meaningful, you're confirming something that's meaningless, which doesn't seem like it adds much value. So I think the same criteria, grounded model, meaningful variables, apply. The question as to whether your model needs to be a black box or not is a little different if you're doing something purely confirmatory. But there again, right? If I've confirmed that there's this pattern, but I have no idea whether or not my confirmation in fact you could have something that's true, meaning and something that's statistically significant. They could align, but not actually be the same thing. So I think the same criteria that I'm describing here are actually the principles of any good research. And even in an exploratory setting, sure, just blindly looking through data first of all, it's fun. We've all done it, right? You have your data and you just start playing around. But I think that there's a trajectory towards more and more informed explorations of the data. And I think the further along that trajectory we go, the better off we are.
Okay. Yep, Phil. We've got a mic running to you now. Save David from repeating everything. Thank you.
Great talk, David. I want to ask a question about debate regarding the big C codes.
Mm-hmm.
As you know, there are lots of ways in which people would develop that lists and the structures among them and so on. How in this approach do you make resolutions when two different lists of big C codes have, for instance, nearly identical statistical properties? Or when one person says, yeah, my statistics aren't as good as yours, but I'm more meaningful.
Yeah, that's a good set of questions. You didn't ask the one which is, what if two people look at the same situation and say, this is the right set of big C codes, or this is the right set of big C codes? One of the key words in all this is interpretation, right? So ultimately, it is very difficult to get away from the fact that somewhere in a model there has to be some interpretive step, and interpretive steps are very difficult to adjudicate. When we do inter-rater reliability, that's actually a form of adjudicating interpretation, right? So we have a code, we have a definition, right? And then unless we literally just have a list of words that we're planning to use, I'm making one interpretation, you're making another, and we're trying to see if they align. The kind of generic answer is that when you have dueling interpretations in any of the forms that you've just described, the best tools that we have available are essentially seeing if we can get consensus among some larger number of people, right? So, you know, if I can show that in fact I have a group of researchers and we can get good agreement on my codes, my interpretation of the codes, and so on, and you can't, well, that's one way of adjudicating. What do you do if there's a whole field that says these are the right codes to use and a whole field that says these are the right codes to use? You know, if you talk to an ethnomethodologist, they would say that the kind of codes I just described are nonsense. Why? Because they're not fine enough grained in the data. We should be looking at the pauses and the hesitations and the intonations and so on. And the short answer to that is that's why we have different fields, right? Is that there's some level of disagreement about interpretation where we each go along our own way. And then ultimately, you know, what matters is going to be whether something is useful, whether your target of use is understanding the data better from a research perspective or students using the data better. And just quickly to kind of add one more piece, none of which I'm entirely sure answered your question, but I think it answered something near your question. So another place that this comes up, obviously, is in automated coding. Right? So here you have one process that is making some kind of, using some sort of statistical or quantitative algorithm to identify codes, and then you have a person who is trying to identify codes, right? And we're trying to make some claim that there's a relationship between them. You know, this comes up all the time, of course, and you're right? There is no way to say that just because we got integrated reliability on this sample, that in fact, when we look at something else, they won't diverge. But that's the nature of science, right? We never actually prove that anything is true. What we do is subject it to a test and show that despite the rigor of the test we've conducted, we can't disprove it. And so we can conduct more and more rigorous tests. The only thing I would add to that is that I think it's very important not to just, well, two things. It's very important not to just look, for example, at the keywords that are produced by something like a topic model and agree that the keywords are the right keywords. That is very much not the same as agreeing that what the topic model is picking up is the same thing that you would interpret. And second of all, it's important, no matter what we do, not to just compare some automated process and one person. All that shows is that the automated process agrees with a person. You actually want two people, or at least two people, because you want to show that there's the meaning making is in some way consistent. And you actually have to have all three of them agree, because otherwise you could have a person in the middle, the coding process on this side, and the other person on that side, and even though there's agreement both ways, these aren't agreeing. So there's a bunch of things that we can do to try and mitigate the question that I think you're raising. We can't actually make it go away in the same way that we can't ever prove anything in an empirical context.
Thanks. Okay, can we have the mic down the front here for Alyssa? Thanks.
Thanks, David. That was a very exciting talk. Not surprisingly, I agree with pretty much everything that is in there about the importance of looking for meaningful findings and the need of both quantitative and qualitative methods to do so. At the same time, we know that's a big ask, right? There's a lot to get up to speed on just on the quantitative data mining side of things. Things are changing, new data sets and all of that. And training in qualitative research is not necessarily something that everybody in the room comes to the table with. And so I was hoping maybe you could elaborate on two things. One is, I think, especially in your diagram, the horizontal lines sort of showed the touch points where we can and should, if we're doing a quantitative data mining kind of study, look back and sort of, you know, step away from the big picture and dive deep in to look at the data ourselves. And so I guess I was wondering if you could talk about A, sort of where you see the most important touch points for that happening, and B, I think with ENA, you've built tools that facilitate that, right? So the notion that if I'm looking at an edge between two words in an epistemic network that I can zoom in to understand in detail what contributed to that. So the ways in which you've built your tool to support this that might be generalizable to other tools to help facilitate this kind of work.
Yeah, so that's a great, again, set of questions. Thank you. So let me say a few things, a couple different things, because there's a couple different questions in there. So one of them is addresses the question of, wow, that's a lot of stuff that we have to do. It was a lot simpler when we were just either doing qualitative analysis or doing data mining. And yeah, it's a big ask, but it's a big ask both because there's big data and because there's a lot on the line when we use it, especially if we're using it to make decisions about students or give teachers information that shapes their decisions about students. You're correct. One way to address this, and I think a very important way, is through a community like this, constructing tools that facilitate that. That is not just taking things off the shelf and using them, but actually thinking about how a tool needs to be reformed and packaged so that it can apply to a particular set of problems. There's lots of examples of this. The cometrics, for example, takes a whole bunch of natural language processing things and puts them in one place that makes them easy to use if you don't do NLP. ENA, we've tried to do something similar. Our next work is actually going to be so that you can upload audio and have it go all the way through the transcription and the coding and go all the way through the model. That's, of course, more facilitating people who are essentially qualitative researchers and getting to the quantitative side, although I believe it actually goes both ways. A second thing I would point to is, well, we don't have the diagram up there anymore, but this is a hugely interdisciplinary community, right? And important work on hard questions tends to not just be done from one perspective. We need not just interdisciplinary, but transdisciplinary work where, people who from the statistics side come to a problem and say, look, I don't do qualitative research, but I get that whatever we do has to be valid from your perspective. And similarly, qualitative researchers who aren't just dismissing statistics, but are saying, look, I don't do the statistics, but I get that there are things that we have to do to make that work. So there's a certain interdisciplinarity. I also think, as usual, the answer's in the future. Whoever in this room is still a graduate student, you're the ones who are actually going to do this. Us old fogies, we're just trying to give you the tools that you need and that you should get trained in both qualitative and quantitative research and in thinking about how they go together. The last piece of your question was about the touch points. I actually think all three touch points are really important, for the obvious reason that if your variables don't mean what you think they mean, it doesn't work. That seems relatively straightforward, although, as I pointed out, there are lots of cases where people who are doing quantitative work don't actually look at all as to whether or not what they've measured is meaningful. I'm just picking words, so I don't have to do any validation. Well, that's pretty silly, right? Then there are qualitative people who say, it's just my interpretation. I don't need to run any of these. I don't need to do anything to validate it. This is just my story. And that can work in ethnographic context too, but it's, again, sort of underpowered and cherry picking. So that's a very important link. The second link that's really important is the modeling link. And what I would say about that is you should be able to justify your model in the same way that Pip asked me to justify mine. That is, you should say, here's what I think is happening. Here's my understanding of the way this phenomenon works, and this model reflects that understanding. It's not just a model that's good for finding stuff, and I found some stuff. And then the third part is the black boxes piece, and this is actually controversial right now. There's people are talking about this a lot in the field, and I'm of the opinion that it is possible to use statistics that are powerful, even if you can't go all the way back to the ground and see what they've done, tensor analysis, for example, stuff like that. It's very easy to cross the line between finding something that's an interesting pattern and telling people to move their pieces faster. And if you're going to use a black box, you have to be very, very, very careful about how you use it, because you can't actually inspect it. You can't point to the causal relationships that it's capturing. Sure.
Okay, guys, I'm going to call break at this point, but we do, of course, have more time afterwards, so go fuel up with some caffeine. David has given us a very rich glimpse of the work he's been doing over a long period. I hope that some of you will come gather down the front after the break, and we can explore this further. But meantime, let's just thank David one more time for that amazing keynote.
Thank you all. I'll be around for the conference, but have a great conference if I don't see you again.